All right, hello again. So in this video, we're going to talk about what you might think of as the opposite extreme from perfect substitutes, which is perfect complements. So whereas perfect substitutes are two goods that we can use instead of each other, right, like larger or smaller boxes of laundry detergent, perfect complements are goods that are only useful when we use them together, and when we use them together in a specific ratio. So the classic example people like to give is right shoes and left shoes. Right, if I have a left shoe but I don't have any right shoe to go along with it, not very useful. If I have a right shoe but no left shoe, that's not useful either. Right, I can really only use shoes when I buy them in pairs. Another example that I like to give is bicycle chains and bicycle gears. Right, if I'm trying to build a bicycle, I need 2 gears for every chain. Right, if I have an extra chain after I've combined all my gears and chains, it's not going to build any bicycles. If I have an extra gear, that's not going to build any bicycles either. So if we think about how to express that mathematically, right, the fact that what we're trying to do when we're buying chains and gears is to construct sets of chains and gears that allow us to build a bike, might look something like this. Right, we might say that our preferences would be represented by a utility function, right, in terms of C for chains and G for gears, where our utility is equal to the number of bikes that we could build, right, the number of sets that we could put together. So what's the number of sets? Well, it's whatever's less, right, or the minimum, between the number of chains I have times, right, I need 1 chain for a bike, so it's the minimum of the number of chains I have, and half the number of gears I have, right, because it takes 2 gears to make a bike. So if I have 1 chain and 2 gears, I should have a utility of 1 because I can make 1 bike, whereas if I have 2 chains and 4 gears, I'll have a utility of 1 because I can make a bike. But if I have some extra chains lying around, it doesn't do anything. It doesn't increase my utility at all. If I have extra gears lying around, that doesn't increase my utility either. Okay, so let's think about what our indifference curves look like when we have preferences like this, right? When our preferences between chains and gears are this min function. So we can graph, right, chains on the horizontal, gears on the vertical. Let's start with, let's say, 2 chains and 4 gears. Right, and we want to know what are all the combinations of chains and gears that were indifferent between that combination and 2 and 4. So what's our utility of 2 and 4? Right, well, it's going to be the minimum of 2 and 1/2 times 4, right, which is, of course, going to be the minimum of 2 and 2, which is 2, right? So how about if I added gear? So let's say I said, what's the utility I get from 2 and 5? Well, it's going to be the minimum of 2 and 1/2 times 5, right? The minimum of 2 and 2.5, which is just going to be 2, right? So if I add gears without adding any chains, I don't increase my utility at all. So I'm on the same indifference curve. And that's true if I had 5 gears, 6 gears, 7 gears, 8 gears, up to infinity, right? Because adding gears without adding any chains doesn't do anything for me. Okay, cool. So what about if instead of adding gears, I added chains, right? So what if I said, what's my utility of 3 chains and 4 gears, right? Well, that's going to be the minimum of 3 and 1/2 times 4 is the minimum of 3 and 2 is just 2, right? So adding chains without adding any gears also doesn't increase my utility, also doesn't move me off of my indifference curve, right? So when I write up my indifference curve, it's going to be this sort of kinked right angle shape, right? That can consist of a vertical line and a horizontal line, right? With a kink point where I've got chains and gears in the ratio at which they're useful to me. And what if I wanted to add more indifference curves? Well, all the indifference curves that I add, right, are going to have a kink at that same ratio of 1 to 2, right? In other words, the kink's going to be when I have 1 chain and 2 gears, right, 3 chains and 6 gears, et cetera, et cetera, et cetera. I'm just going to have a bunch of indifference curves, all of which are right angles, all of which kink at the same ratio. Awesome. Okay. So what's that ratio going to be in a generic or general sense? Well, we could write a generic perfect complements utility function, right, as u of x and y is going to equal the minimum of some a times x and some b times y, right? We're going to say that kink's going to happen where ax equals by, right? In other words, where we have x and y in the useful ratio. If ax was bigger than by, right, that would mean that we have some useless x's, we'd be on the horizontal part of our curve, right? If by was bigger than ax, we'd have some useless y's, we'd be on the vertical part of our indifference curve. So we can say ax equals by at the kink, right? And so then if we want, we can say y is going to equal a over b times x. That's going to describe that dotted line entry, right? So we're going to have a dotted line that is given by y equals a over bx, and all of our indifference curves are going to kink right along that dotted line. Now, one thing I want to point out that can be a little bit confusing is that what this means is I buy more y, the bigger a is, and the smaller b is, right? So if I have a large coefficient in front of x, I buy more y. If I have a large coefficient in front of y, I buy more x. And the reasoning behind this is maybe a little easier if we look back to the bikes and chains example, right? Where we said min u of b and c is going to, gears and chains, right? Chains and gears, c and g is going to equal the minimum of 1 times c and 1/2 times g, right? The coefficient we had in front of g was smaller because of the fact that we need more gears for each chain. So if we wanted to, right, we can multiply this whole thing by 2 to make things a little simpler. We would say min of 2c and g, right? And then essentially our A tells us how many gears we need to make a set, and our B tells us how many chains we need to make a set, right? So this is a somewhat counterintuitive thing. The bigger the coefficient in front of a good in a perfect complements case, the less of that good we need. Okay, so given this, how are we going to solve problems with perfect complements? How do we find our optimal choice? Well, let's imagine that I drew some random budget constraint, like this one, right? That had a slope of price of x over price of y. This is x and this is y. Well, in this case, right, our optimal choice has to be here, right? The way that I drew it. How do I know that that's our optimal choice? Because everything above that indifference curve, right, is outside of our budget constraint, isn't affordable to us. Every other point on our budget constraint is below that indifference curve, right? So this has to be our best choice. In this case, it just so happens that our best choice fell along the kink of one of our indifference curves. Is that always true? Well, let's imagine that I drew a slightly different slope, right? Still going to be through the kink. What if I drew a budget constraint like this? Right through the kink. If I drew one like this and I look for the best choice, it would have to be on an indifference curve on that kink. And the reason that this makes sense, right, the reason that no matter how we draw our budget constraint, we're always going to be consuming y in this ratio y equals a over bx, is because if we consumed more y than that, the y would be useless. If we consume more x than this and less y, the extra x would be useless. Right? Another way to think about this is if we think about the marginal rate of substitution, right, at various points on our indifference curve, if we're somewhere off the kink, right, if we're somewhere above the kink, where we've got more y than the kink would suggest, then our MRS is going to be infinity, right? We have a completely straight line. The slope of this line is infinite. And that suggests that I'm willing to give up any amount, y for x at any ratio in order to get a little more x, because y is useless and x is useful. And if I was anywhere in the horizontal side of the kink, right, where I have more x than y than the ratio would suggest, then my slope is completely flat, right? My MRS is equal to 0. I am not willing to give up any y to get any amount of x, right? You can offer me infinity x per, 700 billion units of x for every unit of y, and it wouldn't change my choices at all, right? I wouldn't be willing to give up any y. Okay, so this is the idea, right? All we need to do to solve these problems is we say we know that y equals a over b times x, and we know that we're on our budget constraint, and that's going to be sufficient. Right, so our first step, which is the equivalent for perfect complements of saying MRS equals price ratio, is y equals a over b times x. And then step 2 is our budget constraint, right? Px times x plus py times y has to equal I, right? We can plug this in for y. So we can say px times x plus py times a over bx equals I, right? I can pull out x, so I can say px, I'm actually going to make this b over bx, so I'll make this b over b times px plus a over b times py, all times x equals I, right? And that's going to give me x is going to equal my income divided by, or I'll say b times my income divided by b times px plus a times py. And what's y? It's going to be a over b times x. So that's just going to be a times my income over b times px plus a times py. So let's think about what this is telling us. What this is telling us is basically, right, b times px plus a times py is essentially the cost to us of buying one set of x and y. Right, we said that we can think about a as the amount of y we need in the set, and b is the amount of x we need in the set. Right, so it takes b, x's, and a, y's to make a set. I over that is the number of sets we can afford. So if I'm going to buy some number of sets, let's say I'm going to buy 4 sets, how much x am I going to need? It's going to be b times the number of sets that I can afford. So that's what we're doing, right? We're saying we're buying the maximum number of sets we can afford, and that requires b units of x and a units of y to do. Mathematically, right, we're just solving a system of equations, right? We have y equals a over bx, and we have an equation that is px plus times x plus py times y equals I, right? And our optimal choice is just where both of these equations are true. Okay, fantastic. So in the next video, we're going to talk about our last set of preferences for today, which are called quasi-linear preferences.